All right, today we're kind of backtracking a little bit. 4.7 goes back to when we were learning integrals as area under the curve, and we started approximating them. This is something we were supposed to do first semester, but we were kind of a day behind, so I put it off till now. But I am coming back to it because it is something that pops up on the AP test quite a bit. So 4.7 is talking about the trapezoidal rule. So like I was saying, this kind of ties in with some stuff we did way back when. So remember when we had that problem that we were trying to find the area under the parabola y equals x squared from 0 to 4. And we did it a few times, approximating it a few different ways. But we started off by using rectangles. So we could do rectangles that overestimated the area, so we knew it was going to be bigger than the actual area. We also did rectangles that underestimated the area, but we used those areas, added them up to get us an approximation. Well, the trapezoidal rule does the same thing, only without rectangles. You guessed it, it uses trapezoids. So let's take a look. The trapezoidal rule says that for a regular partition of any interval from A to B, so regular partition means that we are breaking it up into equal parts. Um, so basically equal subintervals. So each little base, really in this case, the height of the trapezoid is going to be the same with n subintervals, each of a width of delta x. So that's that regular partition we're talking about. We're taking a whole interval and breaking it up into a certain number of intervals. So if we're trying to approximate the definite integral from a to b of f of x, it's approximated by this rule, which looks kind of crazy, but we'll see that it kind of simplifies a little bit, and there's a kind of a shortcut to it. All right, so going back to geometry, let's look at what the area of a trapezoid is. Anybody remember? It is 1/2 times base 1 plus base 2 times the height. So if you look at this, although it looks a little bit more complicated, that's really what we have in here. We're taking the sum from k equals 1 to n of 1/2, same as over here, times f of x sub k minus 1. Well, that's going to be our base 1, plus f of x from k, that's our b2, and our delta x is our height. So all this is saying is we're taking the sum of the area of all these rectangles. So let's actually look at an example. We can go back to that one that we talked about before. We're going to approximate the function, the definite integral from 0 to 4 of x squared dx. So although we know how to do this now, we're just going to get a little practice approximating, because again, like I said, this is something that pops up on the AP test quite a bit. So if we're taking this, let's look at the graph over here. We've got our parabola y equals x squared, and we're going from 0 to 4. For our example, we're going to go ahead and say that we're using 4 subintervals, so we're n equals 4. The problem will tell you that, and we're just kind of making this one up as we go. So it is breaking up into 4 subintervals. We're going from 0 to 4. There's our a and our b. So to find delta x, we're just taking 4 minus 0 over 4. So delta x is 1. We're going to break this up into 4 little subintervals. 0 to 1, 1 to 2, 2 to 3, and 3 to 4. And now, instead of doing rectangles like we've done before, we're going to create trapezoids. So if we look kind of over here, let's look at the one at the end first. Between 3 and 4, we're going to take the point right here where x is 3 on the graph and the point where x is 4 on the graph, and we're going to connect those 2 points, and we've created a trapezoid right here. Right, do the same thing at 2 and 3. We create another trapezoid. 1 and 2, we get another one. And then 1 to 0, we actually end up with a triangle this time, which tends to happen on occasion. But that doesn't make any difference in our formula. It's still going to work out just fine. So here we go. We've got 4 trapezoids, so-called trapezoids, because this is a triangle, and we're going to use those areas to approximate the area under the curve. All right. So if we're looking at this formula, 1/2 times f of x sub k minus 1 plus f of x sub k times delta x. Well, let's look at the first one. We're doing this for each one of these shaded regions. So our first one, we have 1/2 times, this is for k equals 1. Remember, we're going from 1 to 4. So for 1, x sub k minus 1, that's actually x sub 0. That's going to be this one back here. Well, basically where x is 0. And to figure out what that is, we're just doing f of 0. We're putting 0 into this function right here, to figure out what that value is. So we've got f of 0 plus f of x sub k. So f of x sub 1, our first x value here. F of 1. So the 0 comes from the first part of the interval, 1 comes from the second part, like the other end. And then we're taking that and multiplying it by delta x. We already figured out delta x is going to be 1. So that's this measurement right here is always going to be 1. Now, if we go ahead and do the second interval, we're going to have 1/2 again. Let me change that color. 1/2 times f of 1, right, because that's the start of our interval, plus f of 2 times the same delta x, which is 1. Then 1/2 times f of 2 plus f of 3 times 1, right, or going from 2 to 3. Need to plug in 2 to find out what this value is right here. Plug in 3 to find this value, right? That's the base 1, base 2. Base 1, base 2 from that shape. And then our last one here, we have 1/2 times f of 3 plus f of 4, all times 1. All right, now we could go ahead and plug in 0. We get 0. Put 1 in, 1 squared is 1. We get to put 1 in again, 1 squared is 1. And we can put all these in and figure this out. But I'm going to leave it like this so we can look at the pattern that's going on. What do all of these have in common? Right? Each one of these has a 1/2 out in front. So what I'm going to do is go ahead and factor out that 1/2. Bring that out in front of everything, because each one has it. Also, each one has a 1. Now, that 1 changes from problem to problem. The 1/2 is always the same, but the 1 changes. That's our delta x. So we can factor out that 1. I'm going to leave it as 1 now, but remember, that's like our delta x for each one of those. Now what we're left with is the stuff that we have in the parentheses. But let's take a look at what we've got. We have f of 0 plus f of 1 plus f of 1 plus f of 2 plus f of 2 plus f of 3 plus f of 3 plus f of 4. Right. We're just looking at all of these that are left after we factor out the 1/2 and the 1. Well, you should notice something there. We have 2 f of 1s. We have 2 f of 2s. And we have 2 f of 3s. But our first one and our last one, there's only one of each of those. All right, if you think about it, as we're finding the areas of all of these shapes, let's say the blue one and the green one, they share a side right here. F of 2 is part of this blue trapezoid, and f of 2, that is also a base of the green trapezoid. So all the ones in the middle happen twice, the ones on the end only happen once. So if we wanted to here, we get 1/2 times 1 times f of 0 plus 2 times f of 1 plus 2 times f of 2 plus 2 times f of 3 plus f of 4. Right, so this is the pattern that we can use for these types of problems. Rather than writing all of this stuff out, we can kind of break it down. This right here, this sum is equal to 1/2, like we saw in our problem that happened in each thing, times delta x, we factored those out, times f of x sub 0, so the very left end of the endpoint, or the left end of the interval, plus 2 times f of x sub 1, plus 2 of f of x sub 2, and so on. So all the ones in the middle are going to be 2 times f of x sub n minus 1, plus just f of x sub n. Really, in the end, we're looking at this right here, x sub 0 is a, this x sub n is b. All right, those are our a and b from here. All right, so when we're doing these problems, we're going to follow this equation in this pattern. 1/2 times the change in x, which we can find over here, times f of a plus 2 times f of the next subinterval. So we start over here at 0. Once we find delta x, we can find these other values. So basically it's a plus delta x goes in here, plus 2 times f of x plus 2 times delta x, and so on until we get to b. So that would be f of 4. If we look down here, going back to this problem, you can kind of see what we're talking about. F of 0 plus 2 times f of 1 plus 2 times f of 3 plus, I think I skipped the f of 2 there, and then just f of 4 for the last one. So let's take a look at a problem here next.